G'day everyone. Here we have a range of measuring tools or measuring instruments. Now these are the kind of typical tools you'd find in a spec shop. Today we're going to have a look at what each one is called and what we would measure with it in a spec shop environment. So we'll get started, we'll go through the most simple tools and we'll work our way up to the more complex ones. And we'll talk about how to read them as well. Okay, so let's go through and talk about how to use each of these tools correctly. Of course, with a tape measure, it's pretty straightforward. We pull it out, we have a lock if we want to lock it off, and we can just measure by reading the scale. There's a few little quirks of these tape measures. This one here, and this one as well, they have a number written on the back. This one says 73 millimeters, and this one here says 76. Now that is the length of the tape measure itself. So if we're measuring against a wall and the tape measure comes up against a stop, we can add 76 millimeters to whatever we read at the end of the tape measure, and that will give us our overall length. It stops us having to bend the tape measure in any way. We can just add that amount to our reading. Of course, we also have a rivet on the end, in this case 2 rivets, and the little clip will move backwards and forwards. It's not worn, it's not loose, it's designed to move its own width backwards and forwards. The tape measure doesn't start at 0, it is compensated by this clip here. The clip itself has a measurement. If we butt it up against a wall, it will move on the rivets this way and compensate for its own position. If we grab something with the end of the clip and pull against it, the clip will move away its own length and compensate for that reading as well. So it ensures we're always starting at 0, whether we're butting up against a wall or we're pulling up against a surface. Next, we have the steel rule. In this case, we have metric on one side, imperial on the other, down to the nearest 1/16 of an inch or the nearest millimeter. Pretty accurate, good for measuring on the fly. Nothing that you'd want to machine against, but of course, a handy tool and very cheap and easy to carry around in your pocket. Now, next up, we have the Vernier caliper. Now, this is a standard cursor type. This is metric only, this one. We have a digital type, which is pretty common nowadays and very easy to read. And we also have a dial type here as well, which is an imperial set. Now, when we're using verniers, we start talking in micron and thou, with 1 micron being 0.001 millimeters. And that's also represented by this Greek letter mu. Mu basically meaning a millionth of, in this case, 1/1,000,000th of a meter. We also talk in thou, which is 0.001 of an inch. This particular Vernier caliper set is good for 0.02 millimeters, also known as 20 microns. That is the smallest measurement we can take with this vernier, but 20 microns is pretty small. Now with something like this, we can measure the outside diameter of something rather quickly and fairly accurately. We can also measure the inside diameter with these jaws here, and we also have the option to measure depth as well. Okay, so when it comes to using the verniers, we'll start with the digital set here. It's a very basic and easy thing to use. We just open it up and we measure, in this case, the journal. We have metric and imperial measurements. A drawback is we can break the screen, as you can see here, and we can also get a flat battery from time to time, but they are very easy to use and the most popular option and very accurate. We can calibrate them to 0 every time we use them. And we can see here we've got 39.92 millimeters or 1.571 inches. Now, when we use this set of verniers here, it's a very cheap set of cursor type verniers. It's metric only, but it should give us the same reading we got with the digital set earlier. We can lock it off and then we can have a look nice and close on that scale to see what we get. So the main frame has the millimeters and the first 0 will tell us the millimeters. So we are almost at 40, but we're not quite there. So we know we're starting with 39 millimeters. And then we use the vernier scale here, which goes up in 0.1 with increments of 0.02 between them. And we can see here we are lining up around about the 9.2. So we've got 39.92 millimeters. And that works the same if we're doing an inside measurement like this one here. We take the measurement nice and tight, make sure we're in the center of the bore of this ABS ring. We can lock it off and have a close look at that vernier scale to give us a very accurate reading of how large that bore is. In this case, the 0 is lining up halfway between 41 and 42. So we have 41 millimeters and then we use the Vernier scale here to find out which of these lines lines up with the main frame of the vernier. In this case, arguably it would be the 6. So I'd be saying we have 41.60 millimeters. And next up for the dial type vernier caliper, this one here is an imperial set. The dial is set in imperial and each increment on the green scale is 0.01. Before we got 1.571 with the digital vernier, and we're getting the same result here. We're over 1 inch, we can see we've got 1.5, and as we count the increments, it's 1.57 and a tiny bit. Now next up, as we get more accurate, we have micrometers. I have 3 different types here as well. We have a 0 to 25 metric, a 0 to 1 inch imperial, and we also have a depth micrometer that is good to 50 millimeters. They all work pretty much the same. Of course, imperial and metric, the scale is a little bit different, and the imperial one is good for 1/10 of 1 thou because it also has a vernier scale, and we'll have a look at how to use that. The metric one is good for 1 micron or 0.01 millimeters, which is still very, very accurate. We use them to measure things like shim packs, where we need to go down to a very small size, usually around about 1 or 2 thou. The depth micrometer does work a little bit differently, and we'll have a look at how to use that as well. The metric outside micrometer. This one's good for up to 25 millimeters all the way down to 0. We use the ratchet here to get the right amount of tension, and then we can lock it off and have a good look at the scale. Now these top numbers on the scale, they are millimeters. The bottom numbers, or the bottom markings, are half millimeters. Each turn of the thimble will move half a millimeter. That'll go all the way up to 50. And we can see here we have 10, 10 and a half, 11, 11 and a half, 12, 12 and a half, plus 22, giving us 12.72 millimeters. Now, as for the imperial outside mic, it's pretty much the same as the metric, except for the scale. We can see the scale looks a little bit different, and each number represents 0.1 of an inch. Each line represents 0.025 of an inch, and each increment on the thimble is 1 thou. So in this case, we have 0.501, and we also have a vernier scale. So if we're a little bit over the 1, which we are, we can have a look and see which line lines up with the number on this vernier scale to give us 1/10 of a thou accuracy. So in this case, we have 0.501, and we line up at the 3. So it gives us 0.5013. Very, very accurate. Not normally you'd have to go that low, but we have the option if we need to. Now, each of these micrometers comes with a tool so we can calibrate for 0. We can see here we're a little bit over 0, so we can turn the sleeve with the tool supplied in order to calibrate it for 0. We just slot the tool into this little hole here. Each of them has the same hole and they have their own tool to suit. And we can turn the sleeve, it's quite stiff, in order to 0 the micrometer prior to use. We calibrate to allow for different temperatures. If it's a little bit hotter, it might be out of calibration, and wear as well, and other things that will throw the micrometer out of calibration. We just turn the sleeve and make sure it's 0 prior to use. And the final type of micrometer we've got here is a depth mic. Now this is 0 to 50, but we use 2 different inserts or 2 different pins. One is 0 to 25 and the other is 25 to 50. We have to make sure we remember to compensate for that extra 25 millimeters if we're reading a bit deeper. In this case, we're reading the depth of this pinion. There's a hole in the end of the pinion. We keep pressure on the anvil and we wind the thimble till it comes to a hard stop. Now in this case, it's a little bit different. We're covering up the number we're about to read. So we won't be able to read the number very clearly, but the scale is the same. We have millimeters on the top, half millimeters on the bottom. So we've covered up the 5 and we're moving our way to 5.5. So we're not quite at 5.5 yet, but we're over 5. So it's 5.11. We can see the 10, so it's 5.11 and a little bit. You could argue it's 5.115, but I'd say for accuracy's sake, 5.11 millimeters would be good enough for what we need. Now, next up, we have these telescoping gauges. Now, if we don't have an inside micrometer, which we won't always have, we can have something like these. They're a lot cheaper to use and they're fairly easy to use as well. They are on springs and we can put them inside a bore and lock them off. Now, that will give us a measurement that we can measure with an outside set of vernier calipers or a micrometer and get an accurate reading of the size of a bore. They're pretty cheap and easy to handle, but they're never as good as an inside mic, in my opinion, but they do the job pretty well and they don't need calibrating like a micrometer would do. Now, this one here is a dial indicator. A dial indicator is a very universal tool. It's great for checking run out on a lathe. This one happens to be on a magnetic base, which is very handy. We can check backlash on a differential like this one here, and we can also attach it to this block. Now, this block is used for checking liner projection or liner protrusion. We want a liner to be sitting a couple of thou above the deck face in order for it to seal against the cylinder head. We can fit the dial indicator to this block. We can fit it to pretty much anything that will clamp around it, and it is a very handy universal tool. Now, this one here is a dial bore gauge. Very similar to the dial indicator, we are using a bore gauge to figure out if a bore is tapered, if it is oval, and what its overall size is. Usually you would set this on a setting tool, set it to the spec of the bore, and when we put it in, we can move it backwards and forwards and see where the dial changes direction, and that'll give us the maximum size of the bore. If we set it to 0 and it goes into spec, the dial should turn around at 0 in every position in the bore. If we have any issues, we may have taper or ovality, and usually used for cylinder bores in engines or hydraulic rams. When it comes to using the dial bore gauge, we need to set up this bottom section using the different attachments. We get it as close as possible to the spec. Now, we know the spec of that bore, so we set it up and we zero the dial to the spec of the bore. We can turn the face or we can move the dial indicator up and down to achieve that. Once we put it in the bore, when we're at an angle, it should read oversize. When we're square, it should read 0. And when we go the other way, we're going back to oversize, because of course reading a bore at an angle is going to be a longer distance. So as we rock it backwards and forwards, we can see the dial just touches the 0 and then it turns around and goes back to the oversize setting. If it doesn't reach the 0, the bore is oversized. If it goes past the 0 before it turns around, so we might have +5, the bore is undersized. And of course, we're checking it in all different positions to make sure that bore isn't oval. If we get oversized one way and undersized the other, or perfect the other way, we know we have an oval bore. And of course, the deeper we go in the bore, that will tell us if there's any taper. If it reads oversized at the bottom, we may have a tapered bore. Okay, next we have feeler gauges. Now, I've got some angled ones here and some straight ones as well. Now, these will have written on them their size in both imperial and metric, and it tells you just how thick they are, and mostly in a spec shop we'll use them for doing a valve lash between the rocker arm and the bridge. We want to make sure that gap is consistent. As the engine heats up, it tends to narrow, and we can check it cold or hot and before and after dyno as well. They will tend to tighten up on dyno as the valves recede into the head. We need to make sure that engine is ready to be sent out with the correct valve lash, and this is how we do it. We use a feeler gauge and we just check to make sure that the gap is 15, 30 or 40 thou, depending on what type of engine we've got. And we use this to get a little bit of drag and make sure that the next size up doesn't fit. So if 15 thou fits nicely, a little bit of drag, and we go and we try and fit 16 or 17 thou, oh, doesn't fit, it must be 15 thou, and we're happy that valve lash is correct. They're relatively cheap, they're easy to fit in your pocket or toolbox, and they do a very good job of checking valve lash. They're also used for checking shim packs and stuff as well if we need to measure underneath the housing, but for the most part in this industry, we use them for doing valve lashes on all types of different engines. Next up, we have a Rockwell hardness tester. Now, we test Rockwell in this case in C, and we have a gauge here where a bouncing ball will tell us how hard a shaft or a journal or any component is. It's important for something to be hard. If it's like a camshaft or a crankshaft, we want the surface to be hard wearing, and if we've had a spun bearing or it's been heated in any way, that material can go soft. A soft crankshaft will not last very long, and we need to make sure the journals are as hard as they're meant to be, and that's what we use a Rockwell hardness tester for. Okay, we have a hammer first. Now, a hammer should be very hard. Let's find out. Now, next we have an axle shaft. An axle should be pretty hard, but I don't imagine as hard as the hammer. Okay, and lastly, we have a mild steel bolt. Now that should be the softest of all. And that is pretty much everything I know about all of this measuring equipment. The feeler gauges and the telescopic gauges are pretty much self-explanatory. I hope this can have helped you. Thank you very much for watching.